So, welcome back, everybody. We hope you had a great weekend. So the topic this week, I'm sorry for breaking up all these nice conversations which you guys are having. It always feels a little bit bad. Now, so welcome back, everybody. And I just wanted to give you a quick overview of what we're going to do this week. And you've probably seen it from the email which we sent as well. So the topic this week, so today is going to be the standard lecture session. And we are going to cover, or trying to cover, some material. And one of them is something which I just run through with the slides, just to show you the mathematical link, so that you don't have this kind of feeling that these relations with the curl and the relation between the potential energy and so on are something which just are like a bolt out of the blue. Then we are going to start with a topic which will keep us busy till spring break roughly, and that's about harmonic oscillations, and that plays a central role in mechanics. And you will encounter this again and again, all over in physics, in electromagnetism, in quantum physics, in quantum mechanics, and so on. So the one of the things we also want to do, and you got a kind of teaser in this homework about the interpretation of the potential surfaces. So we are going to look a little bit more into that. And the potential we're going to look at is the harmonic oscillator potential, which plays a fundamental role in physics. It's a, or I should rather say, it's a potential which is an approximation to how we believe physics looks like for the low energy states of a system. Then on Wednesday, we are going back into this kind of split mode, but Julie is going to show us a little bit more how we can write code in a smarter way, so we can make things a little bit easier for ourselves and reuse code when we are writing the different or solving the different homework exercises, because you probably notice now that what you did in homework 3, what you did in homework 4, you were reusing much of the same machinery. And you're going to do exactly the same in homework number 5. The only thing which changes in homework number 5 is that we have a slightly more interesting problem, and that's the Earth-Sun problem. So this, I guess, is one of the first times you meet a more interesting physics case, and many of you are doing a major in astronomy and astrophysics. So this is a typical system which you encounter in the very beginning when you take an astronomy astrophysics course. And we are going to see how we can reuse homework number 4 by just changing the acceleration. And that's extremely useful. And that deals a little bit with code reusability. And we are going to look at algorithms which give us an energy conservation. The Earth-Sun system is a system where energy is conserved, linear momentum is conserved, and angular momentum is conserved. But you will experience that Euler's method, and many of you saw that already in homework number 4, that when time went on, your results looked a little bit strange. So you had a kind of feeling that there's something wrong with Euler's method, because the Euler's method depends on the truncation, a mathematical truncation in a Taylor expansion. So the Taylor expansion is not the same as the textbook author. There's another Taylor, and many Taylors here actually. But what we're going to do on Wednesday is also to change Euler's method by a simple manipulation of Taylor expansions. So many of these central algorithms for solving differential equations, they're just based on manipulations of Taylor expansions. And there's a very powerful algorithm which includes just simply some more function evaluation, just some few ones, which is called the velocity valet. And that gives you a solar system or an Earth-Sun system, which is going to be stable over time as you integrate. And that's very important. Then Friday, we are actually going to, again, work on the problems, on the exercises. And there are some reading suggestions here. So today we're going to look a little bit more into 4.6, but we're also going to look more into 5.1 and 5.2. And on Wednesday, it's chapter 4.8 in Taylor's textbook, which is more relevant. But we are going to tailor that one to the Earth-Sun problem. Any questions about the week? Everything looks okay. Everybody's excited about solving the Earth-Sun problem. I was the first time I did it. Okay, so the first part of the lecture is going to be a little bit me abusing a little bit on slides, because you've seen this in the math courses. So I hope you can forgive me if we just go through that material. Probably you saw that in a multivariable course in mathematics, but this is just to conclude a little bit of discussion about forces and conservative forces in particular. So one of the things you may have seen is actually the link between a line integral, which we have down here. So what we have now is a path in space, and this is represented by an arc length of s. So it means our position then in 3 dimensions is then a function of the length of the arc, which we are integrating along. And then we are going to have a function where we integrate along this path from A to B, where we integrate this function f. So where we have 2 initial points. So one of the important things with a conservative force is that the final result, which to us gives us the so-called work energy theorem, that is something which is independent of the path we take. So the result depends only on the end points. And that's extremely crucial, actually. The thing which we did then is, so what I'm doing now is actually, we didn't do that. We have been using these results from mathematics. So you could define a function, f, g, and h, which are functions which are defined and continuous in a domain D in space. Then a so-called line integral, like the one we saw in the previous slide. So this is normally called a line integral. You're integrating along a certain path. So they are normally called line integrals. In this specific case, it was just an integral along this arch S. Now, that type of line integral is said to be independent of the path in D if for every pair of endpoints A and B in D, the value of integral is the same for all paths C in this domain D, starting from a point A and ending in a point B. That means that the integral depends only on the integration limits and not on the path which is taken. So you will find all this material in the slides. So if you look at an expression, so there are some statements in this multivariable analysis. So I'm taking a little bit for granted that you've taken a math course in multivariable analysis. So if you have not, I mean, just believe me, or rather, I've actually taken this from a standard math textbook. So this is not something which I've cooked up. So you would find this in a standard textbook in multivariable analysis. And then you could then have an expression of the form where you have a function f multiplied with d of x and g and h. And these are functions which are defined in this domain. And this is called normally a first order differential form in 3 variables. And this form is said to be exact if it is the differential of a du. So this f is something we have to recognize as the derivative of function u with respect to x, or function u with respect to y, and du dz, sorry. And so there exists a function u everywhere in D that is now given by this expression which we have up here. So it is said to be exact if and only if we can do this, what is set here, everywhere in that domain. So these are the kind of assumptions which are made in order to derive this result about the independence of the path. In our case, this V is going to be the force. No, sorry, this U is going to be the force which acts on an object. So these are just some mathematical assumptions. Then, what you can prove then is that this relation is exact if and only if the vector function f, which we have here, is the gradient of this function delta u here. So if this function f is now equal to the gradient here, then this is an exact statement. And you can prove that mathematically. So I'm just stating what you can prove mathematically. And this is a kind of reminder of what you may have seen. I'm not showing you the proofs and the theorems, I'm just stating the results. This is often the way we proceed when we do physics, is that we take a theorem from mathematics and we use it. So I'm not proving these statements for you. I hope you can forgive me for that as well. So you can show that this is actually exact if this function f here is exactly equal to the gradient of this function u. And then in this case, you can state the path independence theorem, which states that with the functions, these functions f, g, and so on, that fulfill these exactness conditions, this line integral, which you have here, is independent of path in D, if and only if the differential form under the integral sign is exact in D. And that's normally what's called the path independence theorem. So I'm not going to give you the proof, but what you can find is that this is any vector analysis, in any vector analysis chapter in a mathematics textbook, you would find that. So if you go into vector analysis, this theorem is actually derived there. So this is more meant as a reminder of what you may have seen. And then what you can show then when you do this is that this guy here is simply du. And now you assume that we have a dependence on a variable s for x, y, and z. That means that what you have then is something which you now can write as something which depends only on the two endpoints. And this last equation here is the analog of the usual formula which we have seen, where this the derivative of f is actually given by this function f of x. And this is the so-called path independence theorem. So if you have these relations, then you can show the path independence theorem. Now, for us, this is extremely important because if we have a force which depends only on the spatial degrees of freedom, then we can actually show this path independence theorem. So that's one of the quantities which in physics has such an importance when it comes to conservation of energy and the way we relate kinetic and potential energy to each other. Then finally, what you can show is that the work which is done by a force is something which we would write like this. And from the path independence theorem, we know that this has to result in a difference between the two endpoints only. And this is exact if and only if the force is the force F is the gradient of a scalar function u. And we call this scalar function, which depends on the position for the potential energy. So we would thus have F, which is proportional to the gradient of this potential energy, which is a scalar. And we normally define this in terms of the negative one, because then when we look at the work energy theorem, we would have the kinetic energy plus the potential energy at a later stage, which is equal to the potential and kinetic energy at the previous stage. So that's why we have this minus sign in front of it, because then we can have the potential energies and the kinetic energies at a given point being equal to the potential and kinetic energies at another point. And then there is additional, this is the final part. We can define the criterion for exactness and dependence of path. And that theorem states that they are continuous functions with continuous first partial derivatives. So this is an important assumption. And these are independent of path if we can make these assumptions here. And this leads in turn, and you may have seen that, to the curl being equal to 0. So this kind of independence of path, where you make these equalities here, that leads to a curl of this object f, which is independent of, which has to be 0. And if you can make these connections, which you see here, then it follows that the curl has to be 0. And we have defined the curl, the force to be equal to the gradient, the negative gradient of the potential. So it's actually the curl of the negative gradient of the potential, and that is equal to 0. So with these identifications, it follows that the path is independent of the way, the integral is independent of the path you take, and the curl has to be 0. So we have the following important results. If we have now a potential which depends only on the spatial degrees of freedom, and you saw that in that exercise, which you did now, that exercise had a potential which gave you energy conservation. But since it had a strange dependence on x and y and z, it didn't conserve angular momentum, and it didn't conserve orbital momentum, no, linear momentum. But what we found with that exercise 3 is that the curl was exactly equal to 0. So it depended only on the spatial degrees of freedom. We could show that the curl was 0, and that leads to potential, which leads to energy conservation, and forces which lead to energy conservation. So now when we move to harmonic oscillations, we are actually going to see something which may not always conserve energy. So if we have something like a friction or some energy dissipation, then energy for a closed system will not be conserved. So the first thing we're going to look at now, this is a prelude to harmonic oscillations. We are going to look at potential surfaces and what kind of physics information we can extract by just looking at potential surfaces. So I'm sorry for going through with slides. I dislike that normally, but this was more to remind you of something you may have seen and the links which are interesting for us as physicists. So as you saw in this exercise, when you saw a potential like the one in exercise 3, you could immediately say this is a potential which depends on the spatial degrees of freedom. Let me check whether the curl is 0. If the curl is 0, you already have a lot of insight about the physical system. Okay, so I'm going to switch to the whiteboard. So let's do that. And Julie and George are online. So if you have questions for those of you online, I mean, just feel free to put questions in the chat. But let's take a look now at the harmonic oscillations. So this is a kind of a prelude to the harmonic oscillations. And I'm going to use a shorthand HO for harmonic oscillations. So this is harmonic and harmonic oscillator, HOs, harmonic oscillations, or just a harmonic oscillator. So we are going to remind ourselves of things like the energy conservation theorem. So that says that energy is equal to the kinetic energy, K, plus the potential energy. I'm not specifying any dependence on X and Y and Z here. So V is a letter I'm going to use for potential energy and K for kinetic energy. So we're assuming that to be conserved. And one of the other things we're going to look at, which is extremely useful, and you will encounter that again in the first midterm, which will be available next Monday, and it's due before spring break. So we are going to look at things like potential energy landscape. And you already encountered that in exercise number 5 in the previous homework. And there we asked you more to reason intuitively what it actually means. So let's bring some system into it and how we can actually go from that potential landscape when we make the plot and infer some physics insights about it. So we, in particular here, the things which are interesting is the limits of possible motion. That's something which we can actually read off from that. We are going to look at something which are called equilibrium points. And then we have something which are normally called stable and unstable points. So the kind of system we are looking at now is a plane harmonic oscillator, HO, in one dimension. And this is probably something you've seen tons of times. It's not the most exciting part. So we have a block which is now attached to a wall and doesn't move in the Y direction, it moves only in the X direction. So we could now think of a kind of equilibrium position. So this is when the spring is not stretched. So when the spring is at rest. So this is an equilibrium position, and we just call it B. And then you could think of stretching this object to a specific distance. So you could now think of stretching this one to a distance x0. So suppose that you stretch it to an x0. That could be this point. Or alternatively, you could stretch it to another position, which we could call x1. Actually, now we are compressing it. We're not stretching it. So the first thing we are going to do now is simply to set up the force. And in this particular force, I'm just going to state the force in one dimension. So we just need to write it like F. There's going to be a spring constant K. There is a distance X minus B. So this is the force as a function of X. Now, this is a force which we immediately see that the curl is equal to 0. So this is an energy conserving force. That's the only force acting on the system. So if you were to calculate the curl like we did last Wednesday on this one-dimensional force, actually in one dimension, you don't need to calculate. It is 0. You can just say it's a one-dimensional force, 0 curl. Now, you can extend this to 2 and 3 dimensions. There is nothing which hinders you from doing that. And you will even then see that the curl is 0. So this is an example of an energy conserving force. That means that since the energy is conserved then I'm going to have a potential V of X plus a kinetic energy. And we know then that when we use the work energy theorem, then we would have a V of X minus a V of X0. Well, let's just call this since I just called the other one let's just keep, let's now change a little bit. I need an X0 which is different. So it's not the same as the red X0. So this is just a point I'm going to put in a graph here. So this X0 is just a given point here. And this is obviously given by the integral from minus X0 up to X. And then we have F of X of D of X. And when we integrate up then with the expression for the harmonic oscillator, what we get is 1/2 of K of X minus B squared minus 1/2 of K times this X0 minus B squared. So we can always now define some kind of reference point. So one thing we could do now is to define that V at X equal to B is equal to 0. So remember now that when we are looking at the work energy theorem, we are always looking at something with respect to a specific value. So it's always a relative number which we calculate. So it's the potential energy in a final position minus the potential energy in an initial position. So it's always related to something. And you are free then to scale the system by just adding a constant. So what you could say now, you could say that V when X is equal to B is equal to 0. So let's now say so. If you do that, then what you can simplify the equations here. So if we do this, it's easy to show that. You can actually write V of X, the potential, which is actually 1/2 of K of X minus B squared. And the force, as we know, is given by the gradient. In our case, this is simply d of X, of V of X. And that becomes minus K times X minus B. So let's make a plot of this now and try to see if we can now, when we plot the potential energy, so we are going to make a plot here, and we have our x-axis. So let me put an x0 here. I have this x equal to b here, and I have x1 here. And then we are saying now that the v at x equal to b is going to be equal to 0. So this is our reference point. So we can always choose it as we want. So you are going to get something which looks like this. This is the potential energy here. Okay. And now we can start analyzing the system. So suppose now that we start here, this is going to be an energy which we're going to call E0. And if we plug it in, we are also assuming now that V0 is equal to E0. So this is just an assumption we are making. So you could think of the object being at rest. And that means that we have an energy which is 1/2 of K of x0 minus b squared. So now I put the kinetic energy to 0 in that specific point. So so we have defined this energy. Another thing which we know here, if we now look at it, so at x0, so one thing we know is that f of x is equal to minus dv of d of x. In this specific point, which we have here, is since x0 is larger than b, one of the things we see is that dv dx is larger than 0. So if we take the derivative of the potential energy, so dv dx is actually given by k of x0 minus b at x equal x0. And we have simply now, if you look at the graph here, we have simply said that x0 is larger than b. So that means that in this specific case, the object here has a potential energy which has a derivative which is positive. It means then that d of f, or f itself, so that means if you take this one, that means that f is negative. So it means that from this energy diagram, you would then see that the potential, no, the force is actually pulling the object back. So think of you now looking at the harmonic oscillator here, or this block, which is sliding back and forth. So you could think of now reaching this point here, and then the force is now going to pull back. Okay? So the force points in the negative x direction. Does that sound reasonable when you just look at the graph here, right? So in that specific case now, the force is pointing in this direction. So we're just making up the graph here. It's still in one dimension. So this is along the potential surface. So the system has an energy, and let's just put this E0 here. Now, when you then reach the bottom here at x equal to b here, what we have defined then is that the potential energy v of x equal to b is equal to 0. Now, since energy is conserved, it means that E at x equal to b has to be equal to the kinetic energy of v squared at b plus the potential energy, which is equal to 0, which comes from this value. So it means that all the energy is equal to 0. All the potential energy is 0, and you have only kinetic energy at that specific point. What is also interesting to note at this point here, at x equal to b, what happens then is that dv of d of x is equal to 0. And remember now that we are now going back to the equation which we have. So remember now that dv dx is given by k of x minus b. So when I go to b equal to 0, then clearly x equal to b, then the potential, the derivative of the potential energy is equal to 0. I have 0 force. I have only now kinetic energy. Then there's another interesting thing here. If you look at the second derivative of v, d of x, what kind of value does that one have? Is it negative or is it positive? If you look at the equation which we have. So we have the first derivative there. What's the value for what's the expression for the second derivative? If you take the derivative of the equation which you have here, what do I get? Yeah? Just k. And we have assumed that the spring constant is positive. So that means that what we have then is just k. So this is k, and this is assumed to be larger than 0. What do we call such a function where the second derivative is positive? You remember that? When you look at the function which we have plotted. So let me scroll up a little bit. When you look at the potential energy here, this type of functions, they have a specific name in the math literature. It begins with C. It's a Latin name. Anyone remembers that? Is it convex or concave? That's a convex function. So with convex functions, you can have a global minimum. So in this specific case, there's only one minimum in this potential. So you can have many minima, and you can be stuck in many minima. But in this specific function, the way we have made the problem, this is a function which has a global minimum. Normally, we call this local minima. So a convex function, that means that the second derivative is larger than 0. And this is extremely useful for us to look at. So if somebody gives you a potential energy expression, and you calculate the second derivative, and you find that the second derivative is larger than 0, that means that you are going to have a minimum somewhere. So that means that you could actually be located here, and then that means that you would have essentially just kinetic energy. Or you can be kicked up in the potential well, and if there is no friction, no kind of resistance here, you're just going to go back and forth here. So up here, the spring is pulling you in. So when we now look at this other side, when we move towards x1, you're going to see that then the force is going to be positive. So the force is actually, you're compressing the spring, and so the force is pulling you out. Yeah, you have a question. So if this, we're going to look at a case now, right after this one, where you're going to have the second derivative, which can be negative. Then you're going to have a concave function. Then you will have a maximum. And that's going to be an unstable point. So you will have stable points and unstable points. And that's extremely useful to look at, because you can have the second derivative being to 0, but that's a point where you can actually roll down into a deeper part of the potential well. So we're just going to see that in just a few moments here. So the case which we have here now is a case where if we now keep moving on the other side, so at this bottom point, we have all kinetic energy. So if we now move to the other side, what you will find is that when x is less than b, and moving towards x1 on the graph, what you will find then, when you plug everything in here again, since the derivative, that means that the f, which is minus dv dx, is going to be larger than 0. So your force is now going to act in the opposite direction. And this sounds pretty obvious, right? Because if you go back and look at your spring, so you could now think on your spring here. At this point, this is when the spring is not stretched. So the spring is in equilibrium position. Now, to x0, you've stretched out the spring. So that means that the spring force is acting against you. Now, when you compress it, then the spring force is acting outside again. So that acts in the positive x direction. Does that sound reasonable? So these are things you can connect. When you look at the potential surfaces, you can connect it to the specific system you're having. And this is this kind of reasoning I want to have you with me, because we're going to use it for the rest of the semester. And we are going to look at this in the gravitational problems and in many, many other types of force problems. So in this specific case, what we have now is a case when we move beyond this equilibrium point. So let me just mark this again. So this point here is normally called an equilibrium point. And this is a minimum, and it's normally called, in this case, a global minimum, because there's only one minimum. So this is a local or global minimum. And since we've scaled the potential, so the potential energy is 0 at that point, it means it has only kinetic energy. Now let's look at a slightly different case, because there was a question here down in the hall here. So if we now move on to a new example, and this is a type of potential which actually people make in electronics. So let's look at a potential like this. We have X here, and now I'm going to draw it so it looks something like this. So this is a little bit closer to what we had in the previous exercise. So we had in exercise 5. So we have the point here, x3, and then we have a point here, which is x2. And I'm not giving you the mathematical expression for it, but what you would see now is a system where if you look at these points which we have here, these 2 points here, and let me just put up here, this is V of X, this is the potential energy. If I give you an energy which looks like this, so let's call this an E0. And let's suppose now that you have fixed the potential energy, so it's been scaled now, so that we have V of X1 is equal to V of X3, and they're just set to equal to 0. This is a scaling we can always do, right? So if we now look at X1 and X2, what should the value of this be? The derivative of the potential. Should it be larger than 0 or smaller than 0 when you are in these 2 positions? If you now spool back to what we did with a plain harmonic oscillator, it should be greater than 0. Excellent. So that means that these 2, no, sorry, it should be X3. I'm sorry for that. It should be X3. So this is greater than 0. So that means that we would call these 2 here, these are called global minima. No, sorry, local minima. They could be giving the same value of the potential as we have defined here. It means that when we now are looking at the force here, now it depends a little bit on the way the forces look like. But what you could think of now, if this is moving up here, then the force would be acting against. You would have kinetic energy at the bottom only, since we said that the potential energy is 0. So if I give it an energy, if we fix the energy of the system to be E0, so what will happen with this object? So think of this being a particle or ball or whatever. So it could be an electron which actually moves in this well here, or it could be you on a roller coaster. So what's your feeling? If the energy is E0, what will happen for the rest of the time, to times infinity? Yeah? Yes, it will just stay in that well, right? So that means that if we now say that the energy is fixed to be E0, energy is conserved. So we're assuming we have a conservative force. So that means that we are just going to oscillate between this point here to the left of to the right of x1, and this other point to the left of x1. So in the exercise which you had, you were actually asked what would be the energy needed in order to get over the potential well which you're stuck into. So one point where you can end up with is actually this point here, x2. This is also a case where you have a minimum or maximum. So in these places, what we have is that dv dx is equal to 0. That happens here, it happens here, and it happens here. But if you look at x2, so what should we expect for the second derivative? If we now go back. So what is your feeling about the value of the second derivative here? Yeah? Yeah, less than 0. So this is a concave, and you see that one here, you have a maximum. So the derivative is 0, so it can be a maximum or a minimum. But the fact that the second derivative is less than 0 means that this is a concave function, and we see that here, right? So the second derivative is less than 0 here. That means, when we look at it, so this is less than 0, that means the following. Since now f is equal to minus dv dx, it means that the df of d of x is actually minus dv dx second derivative, and this is larger than 0. So at that point on the top there, you're actually applying a force which has now a derivative which changes in the positive direction. So you're applying force to the object on the top. So this position here, since there is a force which is being applied to it, it means that this object can be kicked either down to one of the wells or to the other well. So since now the force, the change in the force is larger than 0, so we have the, so keep in mind now that at x2, at x2, then dv dx, this is a maximum or minimum that's equal to 0. So the force itself is equal to 0, but the change in the force is positive. So there is a positive change in force there. So, however, but df d of x is larger than 0. So that means that the force changes and the system becomes a so-called, not a stable minimum, but an unstable minimum, because you can kick it down to one side or to the other side. So that leads to normally what is called an unstable point. Unstable maximum. Or unstable, just an unstable point. So it means that it's going to be a place where your object now can tilt either back here again, or it can tilt into the other well. So you have enough energy now that you can actually get out of the potential well. So in this, if you go back to the exercise we had in the previous homework, you found the energy which was needed for you to escape from the potential well. So if you didn't have a potential well here, which is shaped like this, which goes up to infinity again, it means that you could actually, if the potential well stopped at this point x2, it means that you would be able to escape it. You would have enough energy to escape the potential well. So when people are making these kind of devices in nanotechnology and in semiconductor physics, they're often setting up the potential differences so that you can trap single electrons in these potential differences between layers in semiconductors. And they actually can manipulate these electrons then and make quantum gates with having electrons which can then be either in the well or outside the well, and they can be bit 1 or bit 0. So that's a technology which is used to make quantum computers. So you can actually, in quantum mechanics, you can actually isolate single electrons in such potential wells. And you want them to live in these potential wells. So if there are some thermal fluctuations which heat up the system, they can actually be knocked out, and then your system becomes unstable. So these kind of considerations which you see here, these are kind of ways of thinking which you will see again and again and again. So if I now give you a potential, so let's try to look at another potential here. So suppose we take a plot of a potential which actually looks like this, and this could be the gravitational potential, something like this. And this is as a function of x. So this is our v of x. If I now give you an energy, which is given by this E0 here, this is the energy you're given. And this energy will oscillate between kinetic and potential energy. So what is your feeling about this system? Will you be able to escape this potential well? No. If I give you an energy, suppose now you have an energy here. Suppose you are here, E1. What is your feeling about the system then? So this is both potential energy and kinetic energy. Remember that. When I'm setting up E0 here, there is potential energy and kinetic energy. So what is your feeling about this system? You can escape. And this is what you will see when we are going to look at say an object, let's say a satellite coming closer to Earth. So when it's getting closer to Earth, depending on the energy it has, it can be trapped in an orbit around the Earth, which corresponds to this one. So that means that you will just go back and forth between two positions. So this is just like the Earth has almost a circular orbit around the sun, right? Almost circular. It's not exactly circular, but there is a minimum and a maximum distance. And this minimum and maximum distances would actually correspond to that one and that one. If this x is the distance between the Earth and the sun, if we were to give the Earth more energy, which I hope we don't get, we could be in this situation here. And then we could either crash with the sun, or we could just escape from the sun. So looking at these kind of potential energies gives you a lot of insight about what you might expect. Any questions so far? So I want you to have me with you. I want you to have you with me. So, this is just like when I say left and right. Guys, I'm more than 60 years and I still don't see the difference between left and right. So exactly. But this is the kind of things I want you to think about, because in many of the exercises, many of the problems we end up with, it's this kind of intuition we want to build up. And when you run many of the calculations numerically, you can play around with different types of forces and different types of systems and see if what you get from your calculation fits with your intuition. Okay, let's see how far we have gotten. Yeah, we're getting close to the end. So I was hoping to, there's a very simple thing, which I'm going to do on Wednesday, before we look at the Earth-Sun system. So because now we've looked at the harmonic oscillator potentials, and we looked at the forces, and we simply said that the force is given by the spring force. So if you look at the force which we put up, we simply stated that the force is given by this expression here. But we didn't derive it. So we just assumed that it looks like that. So on Wednesday, there's actually a simple way to derive it. What we're going to do is to make a Taylor expansion of the potential. And then you can derive that force. So to show that the harmonic oscillator potential force looks like that is based upon a Taylor expansion around a minimum. So you take the harmonic oscillator-like potential and you derive a Taylor expansion. And then you can actually derive the form of the interaction and the force. So it's extremely simple. There's nothing more fundamental than that. From a mathematical point of view, it's pretty easy. We should stop here. Feel free to hang around. I mean, probably some of you have questions you would like to ask us. We are hanging around till 5 o'clock as normal. So, but if you have other things you need to do, feel free to do that. Right? And then see you all, guys.